Good evening, everyone. Welcome to our open house from Tortugas Mountain Observatory. Pleased that all of you could join us tonight. Hopefully we'll have a good time looking at the moon, which is the subject of tonight's episode. For those of you who have been in these before, maybe you're starting to get an idea of the routine. And for those of you who are here for the first time, welcome, and hope you enjoy our little program. We have a few more people co-hosting with us tonight. So I'd like to start off just by introducing our hosts. I guess I'll start with me. My name is John Holtzman. I'm a professor and the department head in the Department of Astronomy at New Mexico State. And I've been here for a while, and I've always been keen on getting this observatory up on the top of Tortugas Mountain operational. And I am actually sitting in the basement of that observatory, and I'm sitting in front of two pictures of Jupiter and Saturn that were taken around here back 50 years ago. So I love showing those. Let's see, quick introductions. We have my intrepid regular partner, Zach Edwards. How are you, Zach?
I'm doing fine. Hello, everyone. Glad y'all are here, and I'm glad to be here.
Great. And what's your position, Zach?
I am the Observatory and Astronomy Lab Manager in the department, so I help out with a variety of things in the department.
And Zach, how long have you been at NMSU?
For 10 months now.
So you've been in the couple times, huh?
Yep, new.
And it's kind of interesting. What was your career before you came here?
Before this, I was actually a middle school teacher for computer science and general science, including physics.
Great. And where are you broadcasting from tonight?
At my house, just north of Tortugas Mountain. So yeah, I'm just chilling in my dining room. Nothing too fancy.
All right. Special guest tonight, Kristen Luxinger. Hi, Kristen. How are you?
Hey, I'm doing great.
Why is Kristen a special guest? Kristen is a special guest. She's one of our graduate students in our program. Is that right, Kristen?
Yep, I am a fourth year graduate student, just finishing up fourth year this semester. So yeah, I'm really excited to be here. I do a lot of my research is on the moon. And so this is a really exciting one to be here for.
Oh, and that's why she's invited, the expert. And actually, we have several experts. And where are you broadcasting from, Kristen?
I am up in Alaska right now. Yeah, so it's a couple hours behind for me still, plenty of sunlight. So I'll be seeing the moon a little bit later in the day, in the evening from here.
Great. Our next co-host is Nancy Steinover. Hi, Nancy. How are you?
Good evening, John. Hi. Hi, everybody. I'm glad to be here.
And Nancy's an old hand at this. Nancy's also a faculty member, right, Nancy? But
yep.
You're more than just a faculty member. What's your track record?
My track record. Well, I used the Tortugas Mountain Observatory as a graduate student when I was at NMSU in the early to mid 90s, and I used it for my research, working with Dr. Rita Beebe. And since that time, I've used several different types of telescopes, but Tortugas Mountain Observatory is one that's always near and dear to my heart. And you'll hear more about this, but we were able to use it more recently, about a decade ago, for a fun science experiment that I think our next speaker will tell you about.
Yeah, no, we're going to get to that later. We're not going to.
Okay. All right.
I heard you learned how to drive a four-wheel drive on this mountain. Is that right, Nancy?
It's true. Yeah, it's true.
Okay, great. Let's see. Our final special guest is Rob Suggs. Hi, Rob. How are you?
I'm good. Glad to be here. I work, where I'm broadcasting from here is my office, my home office, where I've been working here for the last year, near Huntsville, Alabama. I work for NASA at Marshall Space Flight Center. And my title there is the Human Landing System Natural Environments Discipline Lead. So that means that I have to describe all of the environments that the Human Landing System, the HLS, we call it, this part of the Artemis program, to send people back to the moon. So I have to document what they're going to encounter there on the way to the moon and on the surface of the moon. So and my connection here is that I was a graduate student at NMSU back in the late 70s and early 80s. I graduated in 84, I think it was. And I guess Nancy and I are academic siblings because my advisor was also Dr. Beebe. And spent a lot of time there in that observatory photographing Jupiter and Saturn on old school photographic plates.
All right, we're gonna come back to that, Rob. I'll give you a chance to
Okay.
about that in a second, just a second. Okay, so that's our host tonight. So we're gonna do our normal routine is I'm gonna switch over to my cell phone. We're gonna go upstairs and open up the telescope dome and take a little tour and head outside, see what things look like outside. It was a little cloudy today. It was a little rain today, believe it or not, just a tiny, tiny little bit, but we'll go see what it looks like.
Okay, are you with me?
Yes, we are, John.
Great, I can hear you. All right, let me untether myself and we're gonna head out into the observatory. We're down at the bottom. There's my little cell basement room with the pictures on the wall that I'm coming from. And so I'm gonna go around. This is the pier of the telescope. The telescope sits on top of that concrete pier, and I'm gonna come around to the steep steps and head on up to the observing floor. Rob or Nancy, you ever fall down these steps? Hope not.
Thankfully, no.
Came close a couple of times.
All right. Late at night, it could be a little something. There's our telescope, our 24-inch diameter telescope, and there are the big observatory double doors, which I'm gonna see if I can open. Right, there we go. Maybe you guys can hear the sound. There they go, opening up. Nice deep blue sky tonight. The wind is kind of blowing out there, so hopefully you can hear me okay.
We can hear you very good, John.
Great, you can see some clouds out there too. All right, so there we're getting open. That's good. And okay, look, there's the guest of honor, the moon. Here's our telescope. I just want to give you a real quick tour. The dome is going to rotate around, and there goes the dome rotating around to where the telescope is pointing out. There's the KRWG tower out there. And light from the moon is going to come in the telescope. Once we point it at the moon, it's going to come all the way down the tube of the telescope, hit a mirror at the base, bounce back up towards the top and hit a mirror that directs the light out to the side. I don't know if you could see, there's kind of that black thing sticking out there with a little red thing on it. That's our digital camera, which is what we're going to be using to take pictures with tonight. So we're just getting that opened up. So we'll now leave the dome floor. That's actually an interesting thing under the red cloth there, which I can unveil. That's actually one of the very first digital cameras used for astronomy. And if it looks big, it's because they hadn't quite figured out how to compactify things so much in those days. This was used. Did you ever use that, Rob?
No, I didn't. That came after my time.
I used it.
Your time, but Nancy used it. Okay, so now we're starting to date everybody. Actually, I guess they already gave you their years. No, Nancy didn't give you her year, so Rob did. Okay, we're gonna head back down and gonna give Rob a chance to reminisce a little bit, because what was going on in the 70s is the digital camera technology wasn't really there, was it, Rob?
No, it wasn't. There were some just linear arrays, I think, during my period of time, but not two-dimensional arrays to do imaging.
So what did you use?
Used photographic plates.
And what's this room that we're visiting here?
The dark room. That's man. It hasn't changed a bit. It's
no, you know, see that bottle of distilled water up there? I think that's a few decades old. So did you used to do your processing of film in here?
Yes, that's right. Yeah, the photographic plates were there were glass plates with photographic emulsion, and we had to take them out, of course, in the dark, and mount them in racks that went in those tanks there to the right that had the developer, the stop bath, and the fixer, and then there was some a washing step, and I think that was it. And then there was a kind of an oven type of a thing to dry them in there as well.
That's this thing, right? That's that thing,
yeah.
Right? Or that's dehydrator. And I'll tell you, you know something, I've always been curious because it's got such a great name. And intermittent gaseous burst valve. You know what that is?
That was to agitate the developer. Rather than stir it or move the plate around, it would burst a little bit of nitrogen through there every few seconds to kind of keep it stirred to make sure you had uniform development across the plate.
Well, that's pretty cool. And I guess those plates were about the size of this photograph. Is that about right?
Well, no, they were I think 3 1/4 by 4 1/4 inches. They were smaller.
Smaller than that one.
Yeah.
And,
That's been.
You recognize the name on this photo, Rob?
Oh yeah, Scott Merle. Yeah, he taught me how to observe. Taught me everything I knew about using telescopes and darkroom work. Yep.
Hey, wait a second. I thought he taught you everything you knew how to observe, Nancy. Is that right?
Yes, he taught both of us.
Scott was a long-term fixture at the observatory and much loved by the faculty and graduate students. I did have a chance to come up here with him before he passed, and he showed me around. It was pretty cool, and such a colorful guy. We still have a lot of his stuff up here because I can't bear to get rid of it. Okay, let's see. Well, heck, you guys can reminisce a little more. The old living quarters, right? And I think you recognize the TV. It's an old black and white.
Yes.
Watch Saturday Night Live on there. I normally observed on Saturday night to give Scott a break. And I remember watching that on that old.
See, it still works. We now use it to try to tune in for extraterrestrials, but I haven't gotten any yet. All right, we're converting this room into a little laboratory room, which I used our last open house, but today we're going to see if we can do something outside. So let us head outside and hope that the wind isn't too bad. See, it's just starting to get dark. Hopefully we got out here quick enough for you guys to get a brief little tour of where we're at. Yeah, I'm looking west right into the wind, looking down at the clusters. Zach, can you tell what that is?
I can see that it is a stepladder, yes.
It is a stepladder, and what's on top of the stepladder?
Light bulb, there we go. Huh.
A light bulb. All right, so good. You're very clever. So Nancy, what do you think that represents?
I can barely see anything in your screen. Is it the sun?
Right.
Okay.
Very clever. Whoa! And there it goes. Sure enough. Okay, so there's my little representative sun. And now what's the stepladder, Zach? That's a tricky one. Can you hear me?
Yeah, I can hear you.
The stepladder is my anti-gravity device that holds the sun up. All right, so my phone is us from the vantage point of the Earth, and the Earth goes around the sun. So here you can see me going around the sun. And you can actually see that if we could see stuff behind the sun, and you're probably having a hard time seeing stuff behind the sun because the sun is so bright, that the sun would appear to pass through different background objects as we do one rotation. And that's the reason what we call the signs of the zodiac, the constellation the sun appears to pass through as the Earth rotates around once a year. And of course, I'm going back to my original position. And of course, not only is the Earth rotating around the sun once a year, but the Earth spins on its axis once a day. So that's me spinning on my axis once a day. And when I'm spun away from the Earth, that's called nighttime. And you can see at this time of year, I'd be seeing constellations of the Organ Mountains. Go back to daytime, and then I go around the sun for a little while. Now the Organ Mountains, which you probably can't see, are behind the sun. They'd be visible in the daytime, and at nighttime, we'd see the constellation of what's going on with the Earth. So now what we want to talk about is the moon. But just a quick introduction. So I'm going to come over here. I got to find the moon. Fortunately, you guys still hearing me okay?
Yes.
There's a fair amount of wind noise.
Fair amount of wind noise, but you can sort of get the point. Otherwise, Nancy, you'll have to guess what I'm doing. Here, I have a moon.
There you go.
So there's the moon. And what does the moon do? The moon goes around the Earth. Right? So here I'm making the moon go around the Earth very fast. Takes about 1 month to go around the Earth. But the interesting thing is, as the moon is going around the Earth, half of the moon is always lit up the half that's pointed towards the sun, but that's not always the half we can see. Like right now, I know you can see the moon a little bit, but the lit up half, I'll move my phone. No, I can't move my phone, my arm's not long enough. Okay, the lit up half is the half that's pointed towards the sun, and we're seeing the unlit up half. This is what we call new moon. And as the moon goes around in its orbit, hopefully you can see, as it comes around in its orbit a little bit, and then you can see there, you just see a little crescent part of the moon. And that's because, again, half the moon is lit up, but from our vantage point on Earth, we only see a little sliver of the half that's lit up. And as the moon continues around on its orbit, that's what we call quarter moon, continues around on its orbit, this is what we call gibbous moon. And finally, when it's on the other side, that's what we call full moon. Whoops, my head got in the way. All right, and then when we come around this side, we have what's called the waning gibbous moon, the third quarter moon, and the waning crescent moon. So the phases of the moon come from the fact that the moon is being lit up by the sun. Half of it's always lit up, but we're looking at it from the vantage point of the Earth, and we don't always see all the lit up half. We go from seeing none of the lit up half to a little bit of the lit up half, to half the lit up half, to more than half the lit up half, to the full lit up half, to less than half, to half the lit up half, and back to Crescent again. How does that work, guys? That demo work?
Yeah, it's good. You can really see the phases that way.
I love it.
It's great. Yeah,
and you
it's
might
great.
wonder, you know, notice that this has nothing to do with shadows. You might wonder, well, how come he's holding the moon underneath the sun? How come he's not doing that? And that's because the moon's orbit is slightly tilted relative to the plane in which the Earth revolves around the sun. So it really is a little below the sun and a little bit above the Earth's shadow here. But at different times of year, as the Earth comes around different times of year, you can actually get to the time when the moon actually does go in front of the sun. And what's that called? Kristen?
That would be an eclipse.
That would be an eclipse. Right. Now, my model here is not quite the right model because my sun is not nearly big enough and not nearly far enough away. But I've kind of got it matched that it turns out that the moon is about the same angular size as the sun. So it just barely blocks out the sun. But I don't have the right proportions here, but I got it doing the right thing. And when the moon comes around the other side, sometimes it comes down into the shadow of the Earth. There it is. And what's that called, Nancy?
A lunar eclipse.
That's a lunar eclipse. So eclipses really do have to do with shadows, but phases, which is illustrated, phases don't have to do with shadows. So there's a quick introduction. And one thing that we're going to come back to, we're going to go inside and take some pictures here pretty soon, is there's an interesting thing when you look, say, at let's look at a quarter moon, right? You can see there's the sharp left side of the moon, the round side, and that side is really fully lit up in sunshine. In fact, on that curved edge of the moon, the sun is almost overhead, and so the sun's shining down directly. But if you look on the less sharp side, not the round side, the side that's kind of got a straight line going down to it, that region is called the Terminator, and that's the region where, if you were on the moon, the sun would be low down on the horizon because it's the area right between being in the sun and being out of the sun. So if we were talking about the time of day there, that's twilight. And twilight is interesting, and it's interesting for looking at lunar features. And I don't know, why does someone think that is? Why is twilight an interesting time to look at lunar features? Rob?
The shadows are longer, so you can see the features better.
All right, so let's keep that in mind, and let's head back inside and actually try to look at the real moon. Back in the building. Now, when you used to observe, Rob, did you have to observe up? I'm sure you did have to observe upstairs on the observing floor, right?
Yes, yeah. We didn't have any kind of remote control. We had to be up there with the camera and actually manually moving the plate so we could put multiple images on one photographic plate.
Similar generation to you, Rob. And when I was in undergrad, I also had to observe out on the floor, and I was in Connecticut, and it was cold. And I had to sit there and stare into a little eyepiece and kind of keep the telescope guided. Did you ever have to do that?
Yes, yeah, we had to do that. Of course, we had the Blue Mesa Observatory back then, and yeah, we had to do hour-long exposures. I remember doing that, sitting at that eyepiece for an hour, carefully guiding on one star, cold, and oh, it was terrible, but it was fun. I loved it.
Oh, way to go, the good old days. All right, let's see what we got here. Little intro stuff, pretty quick, while we're waiting for it to get fully dark out. Let's see, what do we got here? We already opened the dome and we checked the conditions. They look good. I like to just have a quick little thing on these open houses, just to kind of give people a quick little tour of the sky. We're in April now, we're kind of in the spring sky. And for me, I kind of see some major features in the winter and some major features in the summer, and we're kind of in between them. So I tried to kind of pick out a few things. If you were with me last month, I talked about in the winter, kind of a prominent feature you could see in the sky is what I call the I don't know, maybe it's called the winter circle. That's what I call it, something like that. These stars that are centered around the constellation of Orion, which is what we looked at last month. And they kind of make a circle. And now that we're in the spring, these are way over in the west. But if you go out just after the sunset, you can kind of see this circle. And I actually just got a newsletter from Sky and Telescope magazine today that talked about not seeing the winter circle, but seeing the spring dome. And that's because if we go much later, the bottom ones will be gone at sunset and you'll see the top half of the circle. So the winter circle gets to double as the spring dome if you look over in the west. And so that's a prominent thing to look at. If you get out real early, you can still see Orion, but not much longer. And I guess the thing, that the real prominent thing that a lot of people know about that's coming up in the Northeast now is the Big Dipper, which is not a constellation per se. It's part of the Greco-Latin constellation Ursa Minor, the bear, but it's just kind of got what's called an asterism. It kind of looks like a dipper, and the orientation of the dipper changes throughout the year. But around this time of year, if you look in the Northeast, then the dipper is sort of standing up on its head, I guess. And a couple interesting thing about what the dipper helps you to find. If you take the handle of the dipper and kind of take its arc and follow it around a little kind of circle, the mnemonic is you arc down to the star Arcturus. Arcturus is kind of a bright red star, and I only mention it because Arcturus is kind of an important star to me in my research. Arcturus is an example of what's called a red giant star, and most of the science that I've been doing for a while now is a big survey that's being conducted with the Sloan Digital Sky Survey at the Apache Point Observatory up in the Sacramento Mountains that New Mexico State operates. And Arcturus is a real important red giant star, and it's bright. And we use it actually to calibrate all our atomic physics measurements to try to understand what stars are made of. So I spent a lot of time thinking about Arcturus. It's actually a little bit of a weird star, but that is a different story. And the other thing that the Big Dipper helps you to find is if you take these last two stars, you can call them the pointer stars, and here they are again, not quite in the same orientation. If you follow those in a line about 3 times the distance between them, you come to a star that's not super bright, but it's kind of an important star for people, for landmark, because that's called the North Star Polaris, the North Star. And it's called the North Star because it happens to be in the direction in the sky where the rotation axis of the Earth is pointed. So as the Earth spins on its axis, the entire sky appears to spin around the point that the Earth's axis is pointed to, and there happens to be a star there. And it's called the North Star. And so if you always find the North Star, that's the direction of north, always. It won't always be the North Star, but it'll be the North Star for our lifetimes. So fun, get outside, always good to look up at the sky. As I've said before, you can get star charts, you can get apps for your phone that you can point up in the sky and tell where everything is. Mars is coming up in the western sky these days, lots of stuff to look at. Sky and Telescope is a magazine sponsored by the American Astronomical Society, good resource. Anyhow, just try to encourage everyone not to always sit inside the building and look at your computer screen like we're doing right now. Okay, what else do we have here? Brief little Tortugas Mountain Observatory history. This telescope was built in the late 60s by the Bowler and Chivens Company. It's a 24-inch telescope, and what astronomers mean when they say 24 inches is not the length of the telescope, but the diameter of the primary mirror, which is down here. And that's important. Why do we measure that as the size? Because basically a telescope is a bucket. It's a bucket that doesn't collect water, it collects light. And the bigger the bucket is around, the more light it collects and the fainter stuff you can see. And so astronomers characterize their telescopes by the diameter of the primary mirror. And these days, 24-inch telescope it's a pretty small telescope by research means. What's the biggest telescope we have associated with us at NMSU, Nancy?
That would be the 3.5 meter at Apache Point Observatory.
Yes, Nancy happens to be the director of. Okay, and so where else? Here we go. So what was this telescope built for? It was built, there's always been a history of planetary astronomy at New Mexico State. And I think the primary purpose for the construction of this telescope was to do monitoring of the planets, because it was built at a time before many of the missions that we're now familiar with actually flew to the planets. And NASA saw the importance in getting a long baseline of imaging the planets before spacecraft went there. It was operated through the mid-90s. Nancy was one of the last graduate students, I think, that used it. And that's about the time when the Apache Point Observatory started going into regular usage, and most of the research usage of the Department of Astronomy shifted over to Apache Point. But it did get a brief little revival for some science about 10 years ago, which we'll talk about later. And then, although it had this idle period of 10 or 15 years, about 10 years ago, we did some work in collaboration with a professional amateur international association called the American Association of Variable Star Observers to get the telescope back into operation and to enable it to be used by computer control and to allow it to be controlled without even actually having to come up here. And we're also working on incorporating the telescope into some undergraduate education and research efforts. We've got an upper level undergraduate class going on right now, as a matter of fact, and they used the telescope about 3 weeks ago and actually detected an extrasolar planet by when the planet, kind of a little mini eclipse, when the planet crossed in front of the star that it revolves around, the star got a little bit dimmer, and they were able to measure that. At least their professor was able to measure that. I'm not sure whether the students have been able to measure it yet, but they're working on it. And the other great thing about Tortugas Mountain is its real prominent feature in Las Cruces. Everyone in Las Cruces sees it. And for 10 or 15 years or so now, the Bureau of Land Management and New Mexico State University have had an agreement to kind of run the site as a recreation site. Some of the land is under the control of BLM and some is under NMSU. And since they put a parking lot at the bottom, there's a couple trails that come up here and tons of people come up here, and every year more and more people are coming up here. And I love coming up here. I come up here a lot, hike up with my wife. I hiked up this evening. I'm going to hike down tonight in the moon. It's a great place to come. And for a while, it was a little embarrassing because the exterior condition of this building wasn't great. It kind of had a foam exterior, and it was just too tempting for people to carve their names into. And so it was not looking the nicest. But fortunately, about a year and a half ago, we raised a little bit of money and we did a renovation of the outside of the building. So it's looking pretty nice. I forgot to show you what the building looks like when I was outside, but it looks nice and white. So that's a brief history of the telescope. What else? We're going to take our pictures. I showed you this when I up there with a digital camera. And so this is not a photograph the way Rob used to take it, nor is it an eyepiece where we're going to look through it with our eyes through it. Basically, there's a little sensor in this camera that is sensitive to light, and it's broken up into lots and lots of little pieces, which are called pixels. And basically what a digital camera does is it detects the amount of light, the number of photons of light that hit each area of the detector, and basically builds up a little map of, hey, at this location, so many photons hit, at this location, so many photons hit, and the more photons that hit, the brighter the object is there. And we then take those numbers and turn them back into brightnesses using a computer screen. And so I think this next slide kind of shows what the picture looks like if we look at one of our digital pictures in closer detail, you can see as we zoom in closer, we can see it's made up of lots of little squares. Those are each little pixel on the detector. And if we zoom in even closer, the pictures don't actually have these numbers written on top of them. I wrote the numbers on top of them with the computer, but you can see the brightest areas have the biggest numbers and the faintest areas have the littler numbers. And all the pictures we're going to be looking at tonight are actually these images that look just like pictures, but they're actually light converted to numbers, converted back into brightnesses. And that's what we're going to be looking at. And light comes in a lot of different forms, which to our eyes we call different colors of light. Although there's a lot of kind of colors of light that our eyes aren't sensitive to. We know the colors of light, the different kinds of light that our eye can see, we know of as the colors of the rainbow. But actually light extends beyond what our eye can see, out past the red part of the rainbow. We have the infrared part of the spectrum, which Rob might tell us a little bit about later, because that featured into the L-Cross mission. And past the blue part, we have what's called the ultraviolet light, the ultraviolet part of the spectrum, and X-rays are out there, and radio is way out the other side. Anyhow, we're going to just be looking in the invisible light, and we're not taking color pictures because our digital detector isn't able to take color pictures. It just takes light, all the light that hits it at any time, and we're going to be using a series of filters, probably just one filter. I think probably we're going to take most of our pictures in red light tonight, but they're going to look black and white, because when you only think of the one color, you can't reconstruct the color. Some other open house, I keep saying this, we'll do color pictures, but gotta save something for later. Okay, so I think maybe we're now ready to start go observing, but I guess one more thing to talk about, which is just to introduce the primary guest tonight, which is the moon. So the moon obviously is extremely visible, has featured in lots and lots of different cultures and different myths. Of course, different cultures have different names for it. We generally call it the moon with a capital M. Moons are astronomical things. Moons are things that go around other planets. And the moon that goes around our planet, we just call the moon, capital T, capital M, although I didn't put a capital T on this one. Sometimes scientifically, the moon is referred to as Luna. And then there's many, many cultures. I could have had names for the moon in many, many different cultures. I chose two. Selene is the Greek name for the moon, or actually the Greek name for what they thought was the goddess of the moon. And this one I don't know how to pronounce because it's Chinese. I tried to listen to the Chinese pronunciation on the web today and I still can't pronounce it. Anyone want to give it a shot? Rob, do you know how to pronounce it?
I've heard it as Shunga or something to that effect, but I'm sure that's not right. But
right, that's what I would have said, and the one that I listened to was not even remotely close to that. Anyhow, that's the Chinese name for the goddess, for the goddess of moon from their culture. And I said, there's many other ones. And I think it's important. I'm trying to, in these open houses, we're doing science and talking scientifically, but all these scientific objects factor into cultural things as well. And I think it's important to draw those connections and to appreciate looking at the sky. So some basic physical parameters of the moon. The moon is about 240,000 miles away, which actually, as far as astronomical objects go, is not that far. If you took the Earth, you could fit about 30 Earths between us and the moon. And Kristen, you had an interesting thing, which I had you take out, but you could tell it today. What's your interesting statistic of how you think about how far away the moon is?
Oh, I converted that into how long would it take you to drive down the highway if you went all the way to the moon? Let me do that again real quick. So highway in New Mexico, 75 miles per hour. Let me see. Did I do that right? Yeah. So that would take you, I think I had a different, I rounded differently. So I'm like, wait, is that the same? It would take you about 133 days to drive to the moon down the highway, New Mexico speed.
There you go. I wasn't expecting you to calculate it. Very brave. But yeah, so 133 days drive, not that bad, right? If you could somehow break away from the gravity of the Earth. We talked about the moon's orbit. It orbits once around the Earth every 27 days. But in those 27 days, the Earth has moved a little bit around the sun. Does it come back to the same location relative to where the sun is? The time between successive full moons takes about 29 days. And of course, that's the period that's close to the origin of what our months are, is the period of the moon. And another interesting thing about the moon is the moon, like the Earth, spins on its axis, right? The Earth spins on its axis once every 24 hours. The interesting thing about the moon is the moon spins on its axis exactly at the same rate at which it revolves. And so it revolves around the Earth. And so what that means is that the same side of the moon is always pointed towards the Earth. And that's not an accident, it's not a coincidence. The tidal forces between the Earth and the moon have pulled it such that it does not rotate relative to where the Earth is. And it's actually pulling on the Earth and gradually slowing the Earth's rotation around. And in a long, long time away, the Earth will be pointed the same side towards the moon, just like the moon is pointed the same side towards the Earth. But it's going to be a long, long time before that happens. So we can actually talk about the near side of the moon and the far side of the moon, because it's always the same side that's the near side and always the same side that's the far side. But you can't talk about the bright side of the moon and the dark side of the moon like Pink Floyd, because all parts of the moon get light. We don't always see the part that gets light. The far side of the moon is the bright side of the moon at our new moon, and the far side of the moon is the dark side of the moon at our full moon. If you remember my little arm waving stuff. Okay. And one pretty interesting thing about the moon is lots of planets have moons. However, usually the moons of planets are a lot smaller than the planets themselves. And while the moon is smaller than the Earth, it's not a lot smaller. It's not as much smaller as many other moons are. What is it, Nancy, roughly? A quarter the diameter? Something like that?
I think that's about right, yeah.
Something like a quarter diameter. So it makes it actually a kind of unusual thing that we've got this big moon. And we'll come back to that a little bit when we talk about the origin of the moon and the effect that the moon might have had on life on Earth. If we have time to talk about that, I better get going. So let's now stop sharing this screen and go to our telescope. But we have a nifty camera, a web camera upstairs that actually has some little infrared lights on it, so we can actually keep it on and watch the telescope without disrupting our observations. So what I think I'm going to start off by doing is first thing we need to do when we do observing is we need to focus the telescope. So I'm going to make some effort to do that. And first I'm going to point the telescope up a little bit higher. Okay, so let's see if we can just hold the telescope to move, and there you can see it moving, and you can see the dome moving, and it knows where the telescope's going to end up. So hopefully we're going to end up with the telescope pointing out the dome. The dome's finished, and the telescope is still working on it. It's up here. We're not quite going to the moon quite yet. What we do to focus is we go to a star and we move the camera back and forth a little bit to get the sharpest image that we can. So I'm going to try to do that automatically, and we'll see whether this works or not. Okay, so I have a little computer program that does this for me. Get it to work. It's called autofocus. Run it. Let's see what it does here. Okay, so what the telescope is thinking about doing is it's kind of saying, hey, where the telescope is pointing, I'm going to look around in a catalog that I have and try to find a nearby star that's bright enough that I can use to focus on. So let's see. When we get to the moon, I'll make these things a little bit bigger. This is our fancy computer control panel, but this panel here is kind of the master control that I use to point the telescope and run little programs. And this window here is the camera program, and here's the camera control. It's taking a 10-second exposure, which now the digital camera is converting into numbers, and its image is going to come up there. There it just came up. And then it just went away. I don't like that about the program. It makes the image go away right away, but it won't do that when we get to the moon. So it's looking around. It says, oh, I found where I'm at. Now I'm going to go to a nice star that's useful for focusing. One thing that'll be interesting here, it's, why do I care about focusing? Because when we look at the moon, there's a lot of detail on the moon. We'll see craters and stuff like that, and having them be as sharp as possible is nice, and you have to be in focus to be able to do that. But there's another thing that's going to affect how sharp an image that we can get of the moon, and that has to do with the fact that our telescope is looking out at the moon through the atmosphere of the Earth. And actually the atmosphere of the Earth, which is just this thin little thing astronomically, can have a significant effect on the light coming from astronomical objects, which comes pristine across interstellar space to us. Then it has to go through a little bit of this Earth's atmosphere. And the Earth's atmosphere is a turbulent medium with winds and stuff like that. And occasionally it can make stars go all blurry, something that astronomers called seeing, something that people can go out at night and see as twinkling of the stars. And so some nights are good and some nights are less good. And we're going to hope for a good night here. But I think the night's not too bad. I can already tell. So here it is, just an image of a star, not very exciting. That's not the moon. The moon is going to look a lot different than that. And it's just moving the camera back and forth a little bit, taking some pictures, and going to try to figure out where it got the best image. So we'll see whether it succeeds or not. It's a very clever program that does this all automatically, but it doesn't always work. But I think it's going to work tonight. Okay, it's coming in close near its focus. It's taking a few images here, I think. Hopefully this isn't too tedious, but part of the idea of these open houses is to get everyone the feeling of what it's like to be an astronomer. And it could be worse. You could be sitting upstairs in the freezing cold. Okay, so good. It found a focus position. It's going to take a few images there and measure how sharp the images are. Okay. So this is good. Nancy, Rob, Kristen, you may appreciate this is reading out here in the last column the full width half max of the image in pixels, and the pixels are about half an arc second. So we're getting actually slightly better than an arc second seeing.
That's terrific.
It's terrific.
Yeah, it's great.
Unusual. Okay, so there, it did it in 2 minutes, faster than I could have done it. And now we get to go point to the moon, what we've all been waiting for. Now, what I've realized by preparing for this is the moon is not the most trivial thing to point at. You say, what's the problem? The moon's huge, should be trivial to point at. But as we did outside, the moon is going in orbit around the Earth. So you've got to account for the fact that the moon is moving. That's okay. But also the moon is kind of close to us, astronomically speaking. So it actually, to point a telescope at the moon, you not only need to know where the moon is in its orbit, but you actually need to know where you are on Earth. Because on one place on Earth, you have to point it in a different direction if you're on the other place on Earth, because the moon is actually sort of close to us in astronomical things. It exhibits a characteristic we call parallax. It's like looking at an object out of your right eye and out of your left eye. It looks like it's in a different direction depending where you're looking at it. So I have to look up on my little sheet here. At 9 o'clock, the moon's going to be at these special coordinates, which I'm going to type in here. This is basically putting in like a longitude and latitude. Hopefully I get this right. 11, 39, 21, and 7:30, 33. 7:30, 33. That's basically the longitude of the moon and the latitude of the moon. And we're going to go there. Now, the moon is kind of bright for a big telescope like this, and not the easiest thing, you'd say, well, we build these telescopes to look at faint things. We actually have this problem sometimes in looking at bright things because our cameras don't have what's called infinite dynamic range. They can only count a certain number of photons, and if you give it too many photons, they just go solid white. They say, I'm maxed out, I can't take any more. So we're going to deal with that. It's nice. We just a couple months ago got a new camera for our telescope, that black thing on the side, and it has two very nice features for the moon. One is it's got a very large detector, so we actually can almost fit the whole moon in one picture, as we're going to see, I hope, shortly. And two, it has a kind of electronics that allow it to take very short exposures. So we're going to be taking exposures of just a few hundredths of a second, I think. And I guess now's the time when we get to do it. So I'm going to dial down the exposure time way down. dial it down to 200ths of a second, and I'm gonna, well, heck, I'm tempted to keep the same filter. We had nice images with that one. And okay, what do you think, Zach? Should I hit the button?
Let's do it. Let's see how well we have it.
Let's see whether I typed it in the coordinates right. It'll be embarrassing if I missed. Let's see. I don't know. What do I got here?
Oh,
Whoa, something's there. Okay, so you can see I'm way zoomed in. So I'm gonna, turns out, oh, there's a couple things that I gotta do. One, I'm gonna make this bigger. Two, I'm gonna make this bigger. And then it turns out we have so many little individual pixels on this detector that I don't have as many pixels on my screen as I do on the detector. So I have to zoom out on this a little bit. Zoom way out to just seeing 1 in every 8 pictures. And now there we go. Maybe I could do a little bit more than that. There we go. There's an image of the moon. And it looks like, you see this all solid white? That's that saturated out, too much light. So my 200ths of a second was a little bit too long. I think what I'll do is go to a slightly different filter. Try to get with my 200ths of a second. Oh, there, now that looks pretty nice. That looks pretty nice. And so you see, we can't quite get the full moon on there, but we can get a good chunk of it. Now, this picture of the moon, a couple things. We could see the, let's see, are you guys seeing a good picture? You seeing it all?
Yeah, looks great.
Yeah, it's
looks amazing.
it's pretty cool.
Yeah, super cool.
So astronomers don't actually usually take pictures of the whole moon. Usually the bigger the telescope, the harder it is to get a wide field of view. So, you're usually just seeing a little piece of something. And here we see almost the whole thing. So a couple things, this round side on the end, that's, the round edge of the moon. The sun is shining in that way. That's in full sunlight. And this area where you can kind of tell it's going from bright to dark, that's that area we call the Terminator, which is if you were on the moon, if you were along there, that's where it'd be sunset. This would be, earlier in the day and noon around here and morning over around the backside, and then there'd be a sunrise on the other side. Actually, I'm not sure if I'm getting sunrise or sunset right, but it would be sunrise or sunset. And so that's this area called the Terminator. Now, what we're looking at here, we're looking the way my camera is stuck on the telescope. South is up and north is to the bottom. So this is actually upside down from how, if you go outside right now and look at the moon, from how you might see the moon. But this is actually, it's not upside down if you were to stand on your head, or it's not upside down if you were looking from the southern hemisphere. This is what the moon would look like. But since people are used to looking at it from the northern hemisphere, I think I'm just going to do a little thing that turns it around, and there, now we have it. Kind of what it looks like from the northern hemisphere. Now, it seems like we're not quite in the middle here, so I'm going to try to move it a little bit, and let's see if we can take another picture with get a little bit better centered up. So, do you guys, any of my co-hosts, ever see things in the moon, see patterns in the moon, see objects in the moon? Is that a no?
I think if you're talking about like the man in the moon or the rabbit and the lady in the moon, yeah, those are much better naked eye. I think those sort of things show up better naked eyes. It's hard to see them at this resolution, but they're there.
Wow. So I don't know. Humans, we can make up anything. So let me try. Let me see. Anyone want to make the man in the moon? You've got an annotate tool. I'll make the man in the moon. It's not actually, it's my man in the moon. My man in the moon has, whoops, I don't want to do that. That's not what I wanted. It's not letting me draw. Do you guys know how to use the annotate tool?
I do not.
Too bad. Anyhow, you can maybe see my mouse. I would say there's one eye, there's another eye, there's the nose, And there's the mouth down there. The mouth is a little bit in darkness. So there's one I could see. Another one I could see that people sometimes talk about, Rob already mentioned, a lot of cultures have seen human figures in the moon. But another thing that seems to be common to be seen in the moon is a rabbit. And maybe if I turn it around this way, maybe you could see the rabbit's head and the two ears coming up and its body. And some cultures have the rabbit playing a drum, which is down there. Or you guys think I'm totally crazy? Anyhow, yeah, people see different things in the moon. So now let's go back to the north up, more common view. Let's see, how do I do that? Not that one. All right, so what are some of the key features on the moon? What's kind of the most prominent thing, Zach, that you can kind of see on the surface of the moon, or variations on the surface of the moon?
So right here in this image, you can see a lot of variation in the colors of very bright and very dark, and you can see a lot of little craters that are interrupting it as well.
Right, so it's pretty clear there are these dark places, and then there are the bright places. So Nancy, why don't you tell us a little bit about what's going on with those? People originally said, hey, those look like oceans, right? And in fact, many of the names of the features on the moon were named from that original idea that these are called seas. Actually, there's one big one that we're not quite seeing because it's not quite full moon yet. This is the one big enough called the ocean of storms, I think it's called. And then these little dark areas are called seas. I think this one is called the Sea of Serenity. Tell me if I'm wrong, Rob. And this one is the Sea of Tranquility. Why is the Sea of Tranquility famous, Rob?
Where Apollo 11 landed.
Right around there, right? Somewhere around there. Somewhere around there, where Apollo 11 landed. The first humans on the moon landed there. So tell us a little bit about, Nancy, about what's going on with these dark and light areas.
Okay, so the darker areas, also known as the mare, are younger regions on the moon. So that's a way that we can look at the surface of the moon and tell which parts are older and which parts are younger. So that's an area that has been sort of resurfaced later on after the moon had formed. When the moon was still cooling, it was still undergoing a lot of impacts. And so it's thought that some pretty substantial impacts, caused lava from deeper in the interior to sort of come up to the surface and cover up some of the older, more heavily cratered regions. And so the mare are representative of kind of younger areas. And you can see that there's not very many impact craters within the mare, meaning not a lot of bombardment happened after they formed.
So you're talking about lava on the moon. Is there like lava on the moon now?
Not any liquid lava.
Well, why not? Why is there liquid lava on Earth but not on the moon?
Well, the moon is what we would call geologically dead. It's not, doesn't have a warm interior like the Earth does. And so it has completely cooled off. And so there's no more lava flowing up from deeper in the lunar interior. It's all cooled off by now. Okay,
because it's smaller, right?
Right.
What's the potato analogy? Right.
Exactly. I use that analogy all the time. So astronomers love food analogies, so I use them as often as possible. The potato analogy, if you have a baked potato, you take two baked potatoes out of the oven, a very small one and a very large one. The large one takes a longer time to cool. And so that's the analogy to sort of a big planet, a big terrestrial planet like the Earth, big solid planet. And the smaller solid planets like Mercury or even something like the moon has already finished cooling over the age of the solar system.
Okay, so one thing you said that the area of the Maria are younger the rocks are younger there than in the other areas. And how do we know that? You kind of alluded to it, and you can kind of see in the picture.
Right. So the simplest way we can know that is just by counting the number of craters in various surface regions on the moon. And so the regions that are heavily cratered represent older surfaces, meaning they've sort of just been sitting there and been subjected to this bombardment over the age of the solar system or over the age of the moon. Whereas the Maria, because they have so few impact craters within them, are indicative of a surface that's been sort of refreshed after the more heavily bombarded areas.
Cool. So how many craters are there on the moon, Rob?
I haven't counted them recently. There are new ones being formed all the time, so the number keeps going up, and that's part of the research that, I've done over the years. But I don't know. It depends on the size limit, because you can go down to micro craters where the very smallest meteoroids have impacted, and so it kind of depends on your size limit. But I don't know. That must be a trick question. I'm sure you have an answer, John.
Oh, I don't have an answer to it.
Okay.
A lot. And what I learned in preparing for this, I hope you guys don't get busy for me driving around the moon while we're talking. Hopefully it's interesting to the audience to kind of see different regions, is that all these craters have names, don't they? Who takes care of naming them? Do you know that? Anyone know?
I assume it's something related to the IAU nomenclature commission or something like that. Do you know, Rob?
I don't know for sure, but that'd be my assumption. Yeah, but I really don't know.
The International Astronomical Union. Here we are speaking in acronyms again. Sorry.
So here's a region of the Lunar Highlands, not the Maria, and you could see just craters and craters and craters upon craters. I was reading some article about how there was a newly discovered crater. I forget what was special about it, but partly it was newly discovered. Oh, I know. It was discovered by one of the missions around the moon because it had been hit by another crater on top of it. And they actually detected it, I think, by a small gravity anomaly or something like that, if I'm remembering right. It's pretty interesting. So anyhow, lots of stuff. So let's see, let's just drive to one particular place. Let's take a look at the Terminator. Because remember what we said was special about the Terminator? Since that's like sunrise or sunset, the sun's low on the horizon, it casts shadows. And so let's see what we can do here. Down here.
And just while you're doing that, we actually had a few helpful astronomers in the chat. Yes, it is the IAU who handle naming the craters.
So here we're seeing these craters along the Terminator, and you can kind of see the shadows, right? There's a bright part and a faint part. And I'm trying to find some particularly interesting craters because there's some that are kind of cool looking and have interesting features around them. Some, let's see, kind of like this one. What crater is that? Copernicus. And what's kind of in the middle of it?
There's a mountain in the middle.
So not all of them, but you can tell some of these, a lot of them have these mountains in the middle. And so what's going on with the mountains right in the middle of a crater? Maybe there's a good one. Who wants to take that question?
I can try. So you'll see some of the craters are sort of simple bowl-shaped craters. It's basically a function of the size of the impactor that hit. And so for the smaller impactors, they make what's called simple craters, which is just kind of a little bowl-shaped depression. But for the larger impactors, they actually fracture the bedrock where they hit, and that causes sort of a sloshing of material from below that sort of rises up in the middle and then solidifies to make that mountain. And those complex craters have a sort of a flatter bottom, so it's not like a parabola bottom. It's just a sort of a flat bottom with a mountain in the middle. Those are called complex craters.
So there's an analogy that I've used, which maybe you're going to tell me is wrong, but I don't know if this is appropriate for conversation, but say you had a round bowl of water, right? Like maybe a toilet, and you dropped a rock or something like that down in the middle of it. The water sometimes sloshed aside, then comes back, and sometimes you get a little kind of slosh back up. Is that a similar sort of physics to what might be happening in a crater, or do I have that totally off?
It's a similar physics, yeah.
So that's kind of cool. So we have personal experience with stuff like that. What else? Some other interesting crater-related features. I don't know if we can really see. Well, kind of missing them here. Let's take another picture. Where's my camera control?
Really beautiful imaging, John. It's really spectacular. It's so fun to see.
Yeah, so let's take another picture. Oops, that's no good. That's because I made that little square. Try again. Okay. Notice something's happened to the moon. What happened to the moon? It moved. And you know why that is? That's because it's actually moving. It actually did move. Let's recenter. Actually, that one would have been a good one. Oh, what part of the moon is this up here, Rob?
That's the southern hemisphere, and that's Tycho right there, right below your cursor.
This one right there, right. And so something you can kind of see in this picture, maybe you could see it. What's this?
I don't remember the name of that one. I don't know. It's got a nice ejecta pattern, but I don't remember.
Exactly. So that's what I wanted to kind of draw people's mind to, these sort of ray patterns that come out of some of the craters. And I think you could have seen it with Copernicus as well, right? And so what's that thought to be? Those kind of little rays that come out of craters.
That's the material that was thrown out during the impact.
So stuff got thrown out and kind of got strewn out there, and it's a little shinier somehow, or a little abraded, so it reflects more light than the darker surface, huh? And I guess I was reading somewhere that sometimes along those rays, there may be, kind of dust-sized particles, but there also could have been rock-sized particles. And sometimes you see lines of craters, which are ejecta from the primary crater. Is that right?
That's right. Secondary craters. Yeah.
Well, that's kind of cool. That's kind of cool. All right. We got any questions from the audience, Zach? Any reactions?
A lot of people really like the images. We did get one question. So we know that we have the dark spots, the mare, which is evidence of lava. But with the presence of lava, how come the moon doesn't have anything like volcanoes or any interesting big volcanoes like we see either here on Earth or on Venus or other places?
You want that one, Nancy?
Sure. So there's no active volcanism on the moon today because there's no molten interior. So everything on the inside has cooled and solidified. So there's really nothing driving that material to try to want to get out from the inside. It's basically just a solid interior.
Okay. Well, oh yeah, there's just one more thing that I wanted to look at since we have such nice images. There's just one thing that I'm kind of interested in doing. So let's see if we can zoom in on some little region. Let's zoom in on a region, something like that. And what I'm going to set it up to do is to just take a continuous series of pictures. Let's see if we can get this to work. No, I don't like this. I'm going to try that again. Oops, yes, no, that's good, that's good, that's no on it. So let's take a box like that one. Let's see what happens. Let's take a bunch of pictures. Okay, so what I'm doing here is I'm just taking a continuous set of 2/100ths of a second images. And what I was kind of hoping to see, well, one thing you can kind of see is you can see the moon is moving. Right? You see every image, the moon is moved over a little bit and it's moving around in the same direction. And that is because the moon is moving. And this was actually kind of an interesting thing that I was doing the other night when I was looking at the moon, which is I was telling you that the sharpness of the images, one has to do with the focus of a telescope, but two, it has to do with the stability of the Earth's atmosphere. And the Earth's atmosphere, I mentioned before, is turbulent. The air is moving around. And when you take very short exposures, sometimes you can get lucky and get a real sharp picture, and sometimes you can get unlucky and get kind of blurry picture. So I was wondering whether we could demonstrate the variations in the Earth's atmosphere by looking at these series of pictures and seeing sharper, blurrier, sharper, blurrier, sharper, blurrier. But actually, I think that we just have a very sharp night, and they're all about the same sharpness. But it's kind of fun to watch the moon go around the Earth and get to look at the craters too. And it's better that they're all sharp than if they go sharp, blurry, 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 sharp. It's nice to have all sharp. Okay, I think maybe we'll call it quits with the lunar imaging and head into the next part of our program, if that's okay. We've got a couple more things to share with you tonight. Let's see, I think I'm going to stop this. So the next part of the program, which I'm going to probably do pretty quickly, but I think it's an important part of our program, and we call story packages. And the idea of this is to tell the story of some people who have been involved in the object that we're observing. And the idea of these is kind of the brainchild of one of our other professors in the department, Maura Prescott. And the idea is to try to tell stories from people who have been involved with space things from a somewhat non-traditional background, or what a lot of our stereotypes are about people who do these things. And so the idea is to try to highlight some people that maybe are have been less well represented by the traditional famous people that have studied this, that, or the other. And a lot of these story packages have been put together. There's a group in the Department of Astronomy called the Inclusive Astronomy Group. And they've been working hard at kind of for lots of different astronomical objects, trying to find some people to talk about that are associated with this object. So I'm going to show real quickly two of these story packages here that were put together by two of our graduate students, Kelly Sanderson and Jody Burtis. One is of a woman who many people actually might have heard of, a woman named Katherine Johnson. And the reason you might have heard of her is she was featured prominently in a movie that came out 5 years ago called Hidden Figures, a pretty cool movie about the space program, the NASA space program. And basically she was an African-American woman that was hired to be what was called a computer. Because back in those days, they didn't have the kind of computers we have these days. And so when people need to do a bunch of numerical calculations, they had a row of people that did the numerical calculations. And Katherine Johnson was one of them. And so she was a pioneer in space science computing in a time when there weren't very many African Americans and there weren't very many women in science at all. And so there's a list. I'm not going to read through all these things of some of her accomplishments. She just passed away last year and did a lot of things. Eventually was recognized in this movie and with the Presidential Medal of Freedom. I like when talking about these story packages to give some quotes of the people. And here's a quote she had: "What good does it do us to go to space? Well, what good does it do you to stay home?" That's actually maybe a controversial one, which maybe we'll come back to, but it's still an interesting one. Some of the challenges that these people face: they needed to be assertive as women, worked 16-hour days. But you can see she was a pioneer for, now we have a lot more women and African American in science, but still probably not enough to be representative of the population. And so someone like Katherine Johnson was, I think, a good pioneer and example. Another woman that was involved in the early space program that one of our students came up with is a woman named Margaret Hamilton, who's still alive, who is one of the lead Apollo flight software designers. Have you heard of these people, Rob?
Yeah, yes, I have. Yep.
Okay, so here I just took quotes. I just took quotes from her again, kind of a lot of the quotes from those times. This was in the 60s. No other women writing software. Then there'd be a few, but not many, always more men. I was the first programmer to join and the first woman they hired. Male engineers were already working, but they were hardware engineers and it wasn't their thing. She added her background. She actually worked at the Massachusetts Institute for Technology, did a lot of software for the Apollo mission. And I probably don't have time to read this quote, but it's kind of a great story quote. It has to do with the fact that, a lot of the women, especially at that time, she had a daughter. And of course, she was simultaneously working and taking care of her daughter. Sometimes she'd bring her daughter to work and the daughter was playing around, hitting some keys, and she actually hit some keys in the wrong way and something went bad with a little simulation. And Margaret realized, geez, this could actually happen. And in fact, in a later Apollo mission, it actually did happen. But because of her daughter, she realized they needed to put in some fail-safe mechanisms to kind of recognize that somebody might hit the wrong button at the wrong time. So kind of a sweet story there. I'm zipping through these faster than I normally would, just to kind of keep us a little bit on schedule. So those two story packages are associated not so much with the science of the moon as with the Apollo program and the space program, which, the moon is kind of one of the few objects that we can talk about human exploration of, or the only object we can talk about we can talk about unmanned human exploration of other planets. But thinking a little bit about the science of the moon, I just happened to run across this article from Nature a couple of years ago. Not that these are necessarily the top scientists that are studying the moon, but I thought it was pretty interesting just to sort of give a picture of what scientists are like today and some of the things they do. And of course, science is an international thing these days. So there are people working Korea, India, China, US, United Kingdom, all around the world working on things. And people work in different ways. I like the story of this woman, Catherine Jai, who studies the moon by studying rocks that have been ejected from the moon that end up landing on the Earth, lunar meteorites. And although she works in the United Kingdom, this is not a picture of the United Kingdom. If any of you have been there, this is a picture of Antarctica. And she actually apparently drives around on a snowmobile looking for meteorites, which is like, wow, that's pretty cool. I guess it's easy to see them against the snow. They're these little dark rocks. You see them on snow. A lot of meteorites have been discovered in Antarctica. But then I thought it was an interesting contrast with this woman. Not all scientists need to go zooming around on snowmobiles in Antarctica. This woman, her quote was, she was on a plane flight. She was watching some movie about Neil Armstrong going to the moon, thought it was pretty cool, but sitting in her plane seat, she was feeling pretty cramped, and she was like, that looks really cramped, that Apollo spaceship. I don't want to do that. So she says, no, I just prefer to just go outside with my daughter at night and look at the moon, and I study it in my office. So there's all different types. This guy is interesting in that he's using radar to look at the moon and has discovered something a little controversial with respect to something that Kristen is going to talk about in a second here, which is water on the moon. Here's a woman that studies minerals on the moon, and this woman studies rocks that have been brought back from the moon. And maybe since I ran into it, since we're in New Mexico, I have to say that, in fact, one of the Apollo astronauts lives in New Mexico, Jack Schmidt. He actually gave a talk at NMSU, I think, a couple months ago. And this article was talking about how she was studying a rock that he brought back from the moon. He's the second to last man to have walked on the moon, and he's the last living man, last man that's still alive that last walked on the moon. There are four still, I think, that are alive, but he was the last one. So I thought that was an interesting New Mexico connection. And he still lives in New Mexico, and he was actually a senator of New Mexico back in the 70s and 80s, I think. Yeah. Okay, but we have another young scientist that's working on the moon, and that's our own graduate student, Kristen. And so I asked Kristen to put together a few things to talk about some of the stuff that she knows about the moon. So you up for doing that, Kristen?
Yep, I'm ready when you are.
All right.
Awesome. So I'm Kristen. I do research on water ice on the lunar poles, and I'm going to talk to you a little bit about what is that water ice, why is it interesting, and I'm also going to talk about the Earth and the moon as a system, and how we can study the moon in order to study more about our own origins as a planet and learn more about how planets work. So if we could go to the next slide. So this is just a cool place to start, I think, which is ourselves, looking at the Earth as a planet, and looking at the idea that the Earth and the moon are this pair, and they've gone through life together for a really long time. If you could go to the next slide. So they experience the same environment, right? They have the same experience of incoming light from the sun, incoming heat from the sun. They have a very similar impact history and water delivery history. So the moon, unlike the Earth, doesn't have water or air to erase its surface records. So the moon, the only thing changing its surface is those impacts. So exploration of the moon could actually reveal details of the shared Earth-Moon history that the Earth has kind of covered up or changed or altered in some way. So the moon is this really interesting, simultaneously partner to the Earth, but also record keeper for the Earth. Could you go to the next slide? So the moon formed, the best, our current best model is the moon formed about 4.5 billion years ago when a Mars-sized planet impacted the Earth. The Earth at the time was extremely young, still very hot and molten, and it when this Mars-sized planet impacted the Earth, it threw out a lot of material from the Earth's crust and mantle. And so that material was in this debris disk around the Earth and eventually solidified into the moon. So the moon is made up of the same stuff as the Earth. And so the material that was collected into the moon is in some way a snapshot of what was the ancient Earth like, not in a what would it be like to live on it sort of sense, but what was it made up of? You know, what material had the Earth collected at that stage? If you could go to the next slide. And so when we look at the moon, and we think about, you know, we have this amazing access to this astronomical object right next door to us. We can literally see it looking up in the sky. And it's this incredible ancient record of the Earth-Moon system history. And it's also this laboratory with a vastly different conditions to anything we have on the Earth. So the moon, we know, doesn't have an atmosphere, doesn't have a magnetic field. So it's this exposed surface interacting with the sun, with solar radiation. And it can, by studying these processes of the surface of the moon interacting with the sun, we're learning a lot about how physics works in a way that we simply can't really do on the Earth because we have this atmosphere getting in our way. So exploration of the Earth is improving our understanding of the effects of sunlight on this exposed planetary surface. And it's also teaching us about the history of the Earth and the moon as a system. So we can look at the history of water delivery to the Earth-Moon system and also talk about the original composition and structure of the ancient Earth. So if we could go to the next slide. So when I say history of water delivery to the Earth-Moon system, what does that mean? So there's water on the Earth. I'm pretty certain of that. You know, we're living in Las Cruces, but even we have the Rio Grande. So yeah, check, water on the Earth. Is there water on the moon? Actually, yes. The moon has water on its surface. And if you didn't know about that, you're not alone. We only actually discovered that about, let's say 11 years ago. That we thought there might be, but we hadn't actually detected any. It's not sheets of ice. You can't go play hockey on the moon. It's frozen ice particles likely mixed into the lunar regolith at the poles. So the interesting thing about this is we don't actually have a great understanding of where the water on Earth came from. We don't think it could have formed with all of the water that it has. It was too close to the sun. It would have been too hot for the water to be available in solid form to accrete onto the Earth. So where did this water come from? It was probably delivered to the Earth after formation. But the moon probably had, or the Earth and the moon would have already had that water when the moon formed. According to recent studies, the water delivery happened prior to the formation of the moon. So the moon should contain all of the same ancient water that the Earth had. And if we can figure out where the water on the moon came from, we might be able to tell where the water from Earth came from. You know, what was its source? Did it come to us from far out in the solar system? Was it a little bit closer to maybe Jupiter? Where did if the water was delivered by asteroids, where did those asteroids come from? And I think that's a really, really exciting chance to know more about our origins in the solar system and, you know, where did all of the things that make the Earth home to us, where did they all come from? What is the history and the story of how did the water get to Earth? So if we could go to the next slide. So how do we know there is water on the moon? Are we sure about that one? We're going to talk a little bit about this later in more detail, but the first confirmed detection of water on the moon was made by the L-Cross mission, which slammed a Centaur rocket into a polar crater, releasing this debris cloud, and the water was confirmed detected within that debris cloud, debris plume, sorry. And Nancy on this call And one of her, at the time, grad students observed that plume from Apache Point Observatory and this exact observatory that we're working with today, Tortugas Mountain, in support of the mission. So that's a really cool tie-in. New Mexico State University was involved in the first detection of water on the moon to some extent, which is pretty cool. So I'm also going to talk a little bit about, I mentioned this earlier, the effects of sunlight on an exposed planetary surface. And this is actually a really weird and interesting part of the story when we talk about water on the moon. It turns out solar radiation interacts with the surface rocks, which have exposed oxygen, and it binds together and forms water on the sunlit surface of the moon. And you may think, okay, sure, but the sunlit surface of the moon is really, really hot, right? The sunlit surface, because there's no atmosphere to protect it, gets extremely hot in the day. And so the water almost very, very quickly will get very, very heated. It will turn into a gaseous form or hop ballistically, and it will migrate all over the surface of the moon. It may land in a shadowed region up at the poles and end up being frozen in on the surface. So this is possibly one of the types of water contributing to the water that's found at the poles of the moon. So when we talk about looking at the ancient water that was on the Earth, we have to understand there is also water that's been delivered since. So I talked about the moon as this amazing record keeper. Well, it does its own thing too. So we have to understand exactly what the moon is doing in order to understand what its original records were. It's like if you're looking at a book that somebody else has scribbled on the margins, you have to be able to know who's doing the scribbling and recognize their handwriting. Otherwise, you won't know what the original author wrote. You'll get confused by all these other scribbles in the margins. And we also really want to study the effects of this solar radiation in order to protect astronauts on exposed planetary surfaces in the future. So when we study the moon, we're looking at this amazing record of the history of the Earth-Moon system. Also, in a very practical sense, understanding what happens on a planetary surface with no magnetic field, no atmosphere, is really, really important if we want to do any sort of human exploration in the future. So if you could go to the next slide. So I talked about the ancient Earth. The Earth already had water in its mantle and crust, and so the moon already had water in its mantle and crust in the same sort of distribution as the Earth, same composition, same type of water. Studies of the water in the L-Cross plume suggest that it comes from a mixture of comets that delivered water to the moon via impact and volcanic sources. So when I say volcanic sources, I mean water that was released via volcanic events into a proto-atmosphere. So this isn't it's a temporary atmosphere caused by a lot of volcanic outgassing. Volcanoes have essentially burped up enough gas to temporarily cause the moon to have an atmosphere, which is pretty wild back when the moon was in the process of cooling down. And so water was present within those gases and ended up being deposited at the poles and getting frozen in and remaining stable for billions of years. So a combination of that original ancient Earth type water in the volcanic sources and cometary water delivered via impact was both types were present in the L-Cross debris plume material, which is really exciting. That's telling us that, yes, the moon absolutely does hold that ancient record. It has water that was original to the Earth-Moon system, and we can try to use that in order to understand where did that water come from? What was the story way back before the moon even formed? So if you could go to the next slide.
I interrupt you for a second with a question. I think it's maybe important to kind of make clear. You're like, oh, there's water on the moon. I mean, it's like you could go there and like dip up a cup and take a drink. I mean, let's talk a little bit more about what this is like.
Absolutely. So it's small ice particles mixed in with the lunar regolith, which is, you can't call it soil because there's no, plants or to make it soil. So it's called regolith, dust and that sort of thing. So it's roughly 6% by mass, small amount of water, especially at the surface. Possibly more water would be buried further down, there's still a lot of debate about that. People don't know, and that's why it's so exciting. You know, we want to find out more about what is the water like deep below the Earth's or the moon's surface. Just what sort of a resource do we have down there? We would have to dig pretty deep, and I don't know that anybody is planning to send the astronauts with, you know, a excavator type thing, but using something like radar, we might be able to answer those questions. How much is actually there? How much is buried deep below the surface?
All right, thanks. Maybe you can up here.
Sorry, what? Oh. So I'm talking about, you know, sending astronauts with excavators. We are actually planning to go back to the moon. NASA is in the process of developing the Artemis mission, which will send, I believe the tagline is "the first woman and the next man," which is extremely exciting. And what are we going to get out of that? You know, I believe it was Katherine Johnson said, you know, what do we gain by going? We gain a lot by going, actually. We learn how to operate in extreme cold and darkness if we're sending missions to the lunar poles, and we're developing technology in order to do that. So historically, human exploration and astronomy in general has been an incredible driver for developing technology. So we actually, as you know, individuals, we gain a lot from going to the moon. It's an incredible driver for that sort of technology development. NASA is planning to put a gateway space station in orbit around the moon, which will provide constant access to the moon and also serve as a launching point for missions to Mars, nearby asteroids, other planets. It's easier to launch something from the gateway orbiting the moon than it is to try to get things in orbit from the Earth's surface. Just the Earth is a lot bigger. There's more gravity to overcome. So that's a possible really exciting thing to bolster all sorts of different explorations. So not just the moon. The moon would then be a gateway to the rest of the solar system. NASA is also talking about putting a radio telescope on the far side of the moon. So that would shield the radio telescope from emission from the Earth. And that would then allow us to study the faint radio sources in the very early universe. So not only are we learning about the ancient Earth, we might also be learning about the ancient universe by going to the moon. So exploring the moon teaches us about our own Earth-Moon system, and it also prepares us for exploring more distant planets in the future and opens up a lot of opportunities for learning about the entire universe. If you could go to the next slide. And like I said, we are going to go back to the moon. NASA is working on that Artemis manned mission. The Viper Rover, which is what I have on the screen here, is supposed to launch in the next couple of years, and that's going to be extremely exciting. It's going to be a rover to the shadowed regions at the lunar pole. So it will be looking for, prospecting for specifically the water ice that I talked about. There's a number of orbiters that are planned to launch, and they will also be looking for that water ice and trying to characterize it. How much is it? How buried is it? And all of this is going to be focused on exploring the lunar polar environment. So we can start to understand, you know, what water ice is present, how much of it is there, and start answering those questions. You know, how much of it is the water forming on the surface, how much of it was cometary impacts, how much of it was original to the Earth-Moon system, and start to better characterize all three of those sources. So it's a really exciting time to be looking at the moon. And in the near future, we're going to be going there, which is really great.
Cool. Thank you, Kristen. So Kristen, what's your research about?
So I'm looking at water ice in interesting locations where you have super shadowed locations during the lunar winter, and then you get a little bit of sunlight during the lunar summer. And I'm interested in really complex temperature gradients and how that affects how the water ice is distributed. So I'm looking at basically the most weird and exciting environments you can find at the lunar poles and trying to understand what does all that complex temperature behavior do to the water ice.
Oh, pretty cool. Zach, have we had any questions come in on any of this stuff?
Yeah, we had quite a few questions. One of the main questions we got is that if there is water or water ice on the moon, we've seen other planets like Mars with water ice. So why isn't the moon red or rusting similar to other places we see in the universe or solar system?
That's a great question. I believe the color of Mars has a lot to do with interactions with its atmosphere. I believe, I'm not positive about that. The moon is a different beast. It doesn't have that atmosphere. It has direct interactions with solar radiation, which causes the gray regolith to turn a little darker. And so that's the primary thing that you're going to see is gray turning darker or covered with lava and turning not black, but very, very dark gray. And so you're really not going to see the same types of material as you're seeing on the surface of Mars. You're not going to see the same kinds of behavior.
Any other good ones, Zach?
One last one is that we know you talked about extreme temperatural gradients on the moon. Why does the moon, and this you already hinted at it a little bit, why does the moon have such very varied temperatures from very hot to very cold, whereas we don't here on Earth?
Right, so we have an insulating atmosphere, right? So the sunlight is coming in and it is warming, it's getting scattered by the atmosphere. It's why the sky is blue, right? The blue light is getting scattered by particles in the atmosphere. The redder light is coming directly through, which is why the sun looks redder or more yellow. Not that you look at the sun, but if you ever see a sunlight or a sunset, it's going to look more on the reds and yellows than it does on the blues and greens. The blues and the greens get scattered out. But what you're seeing there is the sunlight is interacting with the atmosphere before it's interacting with your eyes, your body, heating you up. There's a lot of interference going on with the atmosphere. And then the atmosphere is also distributing the heat across the entire planet, right? So you're going to get not much of a difference between night and day compared to the moon, where you can have differences of hundreds of degrees between night and day. There's no atmosphere to smooth out that heat or thermal gradient.
Good question. It's about the same distance from the sun is.
Yep. Yeah, they should be getting about the same amount of heat, but you get vastly different experiences standing on the surface of one versus the other.
Right, great. So let's see, for the audience out there, we've crossed our nominal 90 minutes, which I like to try to keep these things contained to. But I think we're going to talk a little bit more. I want to talk to Nancy and Rob a little bit about the L-Cross mission. But if people are losing their patience, we all understand that. But let's talk a little bit about L-Cross, Nancy and Rob. I think I put together some slides. So I think maybe this one, well, anyhow, I'll let you guys talk to it, but I think you guys were at two different locations. And I think this picture is the location that Rob was at. Is that right, Rob?
Yeah, that's right. That's Tortugas Mountain right there. Same telescope. It ought to look very familiar. I was there with a couple of grad students at the time, and Kat and Ryan, I believe it was. We had the camera that we were using on the telescope there is at actually a different location on the telescope. You can see it down there. That's called the Cassegrain focus. And so we were getting a lot smaller portion of the moon illuminating the chip of our camera. And in this case, we were using a near infrared camera. This is a camera that we had procured here at NASA's Marshall Space Flight Center to use actually to watch meteoroids impacting the moon. We see flashes. We've been doing that research since about 2006 and have something over 400 impact flashes we've seen. And so that's what that camera was for. But we wanted to also try that out on the L-Cross impact to see if we could see the ejecta plume. And so that's an image there from Tortugas Mountain. It's actually a series of images that have been stitched together. And I don't think the seeing was quite as good when we were doing this. This was before the event, about a month before. But we used that lucky imaging that you were talking about, John, where we were running video, 30 frames per second, and we used software that went back and found all the sharpest images and added them all up and registered them, and then they were all stitched together. And I think Chaz Miller, as mentioned earlier, there did put this image together, and this was the astronomy picture of the day back in I think it was October of 2009.
And so tell us a little bit again, what was this L-Cross mission? What happened? What was the idea, and what's special about this place?
Yeah, that place, that crater Gibbous, is near the South Pole, and that's one of those permanently shadowed regions because of the orbit of the moon, and that's crater's proximity to the South Pole. Sunlight just doesn't shine down in there, and so it's a cold place, a cold trap that would trap water. And there have been some other instruments that indicated that in that region there was probably water mixed in with the regolith, like Kristen was talking about. So that's why that location. L-Cross was it was actually the upper stage of the rocket that put Lunar Reconnaissance Orbiter into orbit around the moon. That was in a polar orbit, and it's still there to this day. Been taking phenomenal pictures. I'm sure you've seen them, or at least go Google Lunar Reconnaissance Orbiter, and you'll find lots of images of the Apollo sites where you can see the tracks where the astronauts walked and where the rovers drove. It's just phenomenal imaging. But anyway, that spacecraft was put there to do lots of science and to do reconnaissance to find out more about the type of places we'd like to send people. And the upper stage of that rocket that put it there was the L-Cross vehicle, and that impacted the moon, and a smaller satellite detached from it just before impact and watched the impact and watched that plume. And I'm sure Nancy can talk about the actual imaging of the plume that was done from Apache Point, where they actually saw it.
Okay, so maybe we'll switch over to Nancy, and maybe you can talk a little about what went on there and what this is a picture of.
So this is a picture of the impact site, where we observed it from 3 different locations, kept checking our watches, kept checking our cameras, kept checking our phones, kept checking our computers. We didn't see anything. And so we thought that we missed it, or we're looking in the wrong spot or something. And so we went on our merry way thinking that, and it turns out most Earth-based locations did not see the plume as was predicted. We thought we would see this magnificent debris cloud, rising up over the edge of the crater. And then a few months later, a grad student who was working with me on a totally different project related to Jupiter, who had developed some computational tools to try to pick out sort of faint signals, or looking for variations in brightness across Jupiter's atmosphere, in fact, said, well, why don't I try using my tools on your moon images and see if I can pick it out. And lo and behold, he did that, and was able to pull out a very faint detection of the debris plume. That was really the only ground-based detection of it. And so then we were able to make an estimate of how much water was in that plume, and then that sort of fed into the beginning of Kristen's project. So it was a really nice group effort.
Pretty cool. And who are the people on this paper?
Paul Stricker is the first author. He was my former graduate student who was the one who was studying Jupiter at the time. Chaz Miller, Ryan Hamilton, 2 other grad students in astronomy. Brendan Hermelin was a colleague of ours who at the time had done some experiments to try to simulate what the plume would look like. I believe at that time he was at University of Hawaii. And then our esteemed Rob Suggs, who's here in the audience, and Mike Sussman was another one of my grad students. So it was a great, as I said, a great team effort.
Almost all NMSU, right?
Yeah.
And so maybe we'll finish up here. Maybe you could finish up by telling us about, since you're the director of the 3.5 meter at Apache Point, is there any continuing work going on related to the moon at Apache?
Yeah, I was hoping to get a chance to mention that. Yeah. So at Apache Point Observatory, we sometimes point that telescope at the moon, which you think it's hard to see something bright with a 24-inch telescope, a 3.5-meter telescope, it's even brighter. But we have a really specialized piece of equipment there that's used for what's called the Apache Point Observatory Lunar Laser Ranging Project. So that's where we have a high-powered laser that we fire at the moon, and it is aimed very, very directly to reflect off of the retroreflectors that were left behind on the surface of the moon by the Apollo astronauts. Recently, they also recovered some Soviet retroreflectors that had been lost for quite a large number of years, and we found them using our laser. And so those measurements are used for a variety of experiments, ranging from trying to understand general relativity to try to refine the moon's orbit around the Earth, and all kinds of fun experiments. But yeah, so we continue to use the 3.5-meter telescope to look at the moon, but with a very specialized piece of equipment for a very specialized experiment.
Cool. Yeah, and it's pretty cool.
Yeah.
On the nights when the Apollo, their acronym spells Apollo, which is kind of cute. And it's pretty cool because you see this big bright green light shining out of the telescope up towards the moon, and they send the laser light up to the moon, lots and lots of photons of light. They travel across space, hit the moon, hit these little retroreflectors, and a few of them come back just a fraction of a second later. And by measuring how long it takes to go from there and back, they figure out how far away the moon is. And this is crazy. They're measuring the distance to the moon to an accuracy of a few millimeters, I believe. And
Yes.
I
I think we were the first facility to reach the millimeter range, so it's pretty exciting.
I like to say I don't usually know where I am to a fraction of to a millimeter.
Yeah.
On the moon.
Yeah.
Okay. I had a few more things that I thought we might talk about, but we've been going for a pretty long time, so maybe we should think about calling it a wrap. But thank you very much for joining us. Any last-minute words from the panel?
I just wanted to say thanks to everyone who attended, and it's always great fun to answer your questions and to talk about things that we love to do. So it's really been a pleasure. It's fun to see old friends and colleagues and current friends and colleagues. So it's really fun.
Okay. Well, thanks to the panel and thanks to the audience, and we will see you next time around.